Okay, colleagues, I think that we can start our seminar. I'm very happy to introduce today's speaker, Grigory Kabatiansky, and he is going to speak about cover-free families of sets. So please, Grigory.
Thank you. Thank you for introduction, especially because I would like to say that probably the better title of my talk will be below how to reconstruct an unknown set from its intersections with properly chosen other sets. And so we will see it in a minute. What does it mean? Okay. Consider the following, in fact, known guessing game. There is a player, say hider, who chooses and hide some subset X from endpoint sets. And we want to find this X, and we can do it in the following way. We ask hider questions in the form, what is intersection of this unknown set X with my set A sub I? And hider gives us correct answers for all I, and this is very important assumption. At the end of the talk, I will return to this. But until the end of the talk, we assume that hider is a honest person and he never lies. So then the question, what is the minimal number of questions which is enough for us to recover any hidden set X? Of course, it depends what type of answers the player will give to us. He can give us cardinality of intersection, and it looks like the best for us option because it gives us the maximal possible information. He can give us yes or no for the answer if a set unknown set X and our set AI intersect or not. And finally, something a bit strange, that the same cardinality, but taken by modulo 2. We see that option 2 and 3 provide us one bit of information. And of course, it's an interesting to understand which of these two bits is, say, more informative. Okay. First of all, we would like to avoid trivial family of questions. I mean, if we just take points from our set and ask if there is intersection or not, and then, of course, in n questions, we will know every set, but it's trivial, and therefore we will think only the non-trivial cases when the number of questions should be smaller than lambda times n, and lambda is constant, which is smaller than 1. If the number of questions is even smaller than constant times n, it's only bigger, it's only better. So, and we assume that unknown set cannot exceed by cardinality some threshold t. But as a marginal case, we will consider, of course, when t is n. So the question is, first question is, what could be the maximal size of such a set, which we can find with non-trivial questions? I mean, when we ask not n but lambda times n questions. And the second, also natural question is, if the cardinality of our set is upper bounded by some constant, then how behaves the minimum number of questions or tests? And so that's what I said. What is better? To know if the intersection is empty or not, or to know the cardinality of this intersection by modulo 2. In both cases, we have only one bit, but what is better? Okay, at this point, if it will be not zoom, but say natural seminar, of course, I will ask the opinion of participants. But, well, you can switch your microphone and say what you think is better. And it will be another guessing game. Guessing for the people who don't know this subject. Who knows, they knows. So, do you have any idea what is better? That's why I don't like Zoom.
I doubt I understood the problem right. It seems obvious that in any case the answer is the cardinality of initial set.
No. No, of course, intersection, we have, no, we have a set X, and we have another set A. And we ask what the cardinality of their intersection. The answer could be in 3 different forms. The player which possesses this set X, he can say as intersection is, cardinality of intersection is 3. It means that there is 3 common points for this.
Sure, the first question is more informative than than second and third. I was speaking just about that the third and second are equal.
So you are right that the first option is the best one, because 2 and 3 is just function of the answer for the first question. My question was what is better if the player will say us if intersection empty or not, or he will tell us something strange, what is the cardinality of intersection, if it's odd number or even number. So let's repeat me the question in this way. What is better? To know empty intersection or not, or to know if intersection is cardinality of intersection is even or odd number?
They are equal because the player who guesses needs n questions in any case, just because pigeonhole principle.
No. It's not true. We will see that fortunately, we will, first of all, you see, I consider the case when by assumption is known that the cardinality of unknown set is not bigger than some threshold t. So imagine that you have a set of 1,000,000 points, but the guessing set is only of 25 points. So no. In this case, you don't need to ask 20. You don't need to ask 1,000,000 questions. You don't need to ask 25 questions. 25 questions also will be not enough.
With the additional information, maybe.
What means additional information? The information is there.
For example, cardinality of the
yes.
of the set. Well, then it makes sense.
Yes, but even if I know only if it's empty or non-empty, or if I know if its intersection is odd or even, then the number of questions which will be significantly less than n. Roughly speaking, I choose this example just from scratch, but nevertheless, let's continue. We have a set of 1,000,000 points, and the chosen set X is from 25 points. Then we will see what will be the answer. I will say you the answer for the case when I know if it's odd or even number of points in intersection. It will be 25 times binary log of 1,000,000. Binary log of 1,000,000 is 20, so it will be 500 questions will be enough to find exactly unknown set of 25 elements. So thank you for discussion, and let me now formulate, and we will return to this because probably you will not be satisfied by the answers. So first, I'm sorry. First of all, something. What is the maximal number of? Or maybe I will go to the second question first because we just discussed it. What will be the number of questions in the case when it's known that cardinality of a hidden set is T or less? In one case, when we know for which I use the sign of addition by modulo 2, when we know intersection by modulo 2 or odd or even, we know asymptotic of this number of questions. It's T times binary log n. What is even better, it's of course asymptotic, but in fact, this is number of questions is not bigger than T times log n plus 1 to be more precise, but cannot be smaller than the same figure minus constant. So in this case, we know the answer asymptotically. For the case when we have the full information, when we know what is the cardinality, the answer behaves in the following way. It's better than knowledge by modulo 2, but not significantly better. Only log, binary log T, or log, usually it will be binary log, except when I use natural log. Only in log times, in log T times better. What is worse, that in this case, we don't know the asymptotic, the upper bound and lower bounds on the number of questions difference in 2 times. And finally, for the most natural looking game, when you ask, you just say, if there are common points between X and my questionnaire is set AI, and the hider tell you yes or no. In this case, the number of questions behavior, we don't know even the asymptotic of behavior. It's enough to have, I'm sorry. There's something what I put in the wrong way. I'm sorry. The log should be on the top here. So it's T square log n, and no, our minimum, it's on the left and this is on the right. If you can follow me, I just mixed upper and lower bounds. But you see that the number of questions can be smaller than T squared divided on log T, and the times log n. We always need to, roughly speaking, we need to pay log n, and then there is standing some function depending on T, on what we multiple. So we know how to do it with T squared log n questions, and we know that it cannot be done better than in log T times faster. So this result was independently obtained in 1982 by Dichkov and Rykov, and by Erdős, and I don't write here. I wrote it in a slightly incorrect way. I wrote it says Erdős et al., but Erdős was not the first author amongst 3 of them. And in fact, they wrote 2 papers. The first paper was about T equal 2. This is already non-trivial. And then the full version was 3 years later. look for the question which I didn't ask before, but it's time to ask it. In the case when we have the full information, the cardinality, and there is no restrictions on the size of the X. I mean, subset X can be arbitrary. Then what is the minimal number of questions? Fortunately, in this case, we also know asymptotical answer. It's 2 times n divided on binary log n. The first non-trivial step was done by Erdős and Renyi in 1963, and 1 year later, Lindström and Cantor and Mills independently, they proved that constant 2 is correct constant here. Erdős later include this example in his book together with Spencer, probabilistic method, and this is last chapter in this book, and last is because of the following, because the whole book is about how probabilistic method is very effective, and it helps us to solve the problem where we cannot come up with better explicit constructions. But in this case, random coding or probabilistic method will give constant 3. So what is not appears to be not correct 1, and explicit construction gives us 2. So it's about the question was asked: if can we find the unknown set in a better way just to ask about every point? Yes, we can. We can, and we decrease the number of questions in log n divided on 2 times. And what is also interesting, what is the maximal size of this unknown set for which we can find this set with linear number of questions, but still less than n. I mean, say 0.999 times n, it's allowed, but not allowed to have, roughly speaking, n. Then for full information, the size is half of n. For addition by modulo 2 or even or odd, it's n divided on 4. And for yes and no intersection, empty or not, surprisingly, square root of n. This unexpected result was first proved by Basaliga. It was used and never published by him. Then it was used by Dichkov and Rykov in his paper, and Erdős et al. Rediscovered by themselves. So you see that that when we ask if the intersection of unknown set with our given set empty or not is the worst question which we can ask unexpectedly. So that's, say, long introduction to what I'm going to talk. Because it's just formulation, you can see that mainly here we either don't know the constant in asymptotic behavior or even don't know exact asymptotic behavior. So now I would like to talk a bit, and it will be some kind of so-called recreational math. The statement, how the problem appears. At least the problem of this problem, which was, Erdős was not the first. It was the paper a year before them, but they have found, this is a very good to use here information theory technique. But people come up with such, say, Olympiad type problem. Imagine that you have n coins. And it's known that a good coin weight is 10 grams and fake coin is 9 grams. And you have an exact scale. So if you put, say, 5 coins on the scale, and you will know the exact weight of these 5 coins. And if it's 48, you know, oh, there are 2 coins are counterfeit. So this realization of this cardinality answer. And so the question is what we should put on our scale. What should be the best choice of these testing sets? Another model which appears later in at first time people do not understand that it's the same, and only when they did something they have found, oh, it was done already by Erdős, Renyi, then by Lindström, Cantor, and Mills. They did it 20 years later in the information theory under the name of zero error capacity of multiple access channel. Consider the following diagram. We have n users, and n can be very big, like as before, 1 million. And only few of them, in my example, only 2 of them are active. And they send their signals through the common channel, and the channel is at common. He did something with their signals. In some sense, they do some operation. Like here, it's a function f between, in this case, x2 and xn. And then here we have a receiver, and he wants to know which users were active. For this purpose, every user at the beginning of the system before start to work, every user received his own binary vector. So when they're active, they send their vectors through the channel. And the question only is what this multiple access channel do with the inputs. For counterfeit coins, it's so-called binary adder channel. He simply add 0 and 1s, which the channel received at every time slot. So that's, of course, it's the same as measurement on the scale. And now, finally, let's go to more mathematically effective way of representing this problem. Consider binary R times n matrix H. And rows A1, A2, AR, in fact, they are characteristic vectors of our testing sets AI. And let small x will be characteristic vector of the set x. Then the result of IF test is, of course, for the considered case when cardinality is just cardinality of their intersection. But it's the same as scalar product of ordinary scalar product as real vectors, but real binary vectors. Therefore, of course, as they have only 0 and 1s, then their scalar product is the number of positions where both vectors have 1s. So this is intersection. So therefore, all results of our tests can be obtained as just a product of our matrix H to this characteristic vector X. And I put it here transposed because the vector X should be column. Then column times row. And I will call this as it's called in quantum theory syndrome vector. So our goal is to construct matrix H such that for different vectors, which has not more than t ones, their syndrome should be different. And it's written here. So let's have a look for first for, I will call it Renyi problem or counterfeit problem. When I have no restriction on the weight of my vector x or on the cardinality of unknown set x. So I would like to establish the lower bound on the minimal number of questions. So the lower bound on the number of rows in my matrix H. So how many vectors, different vectors x or y we have? Of course, 2 to the power n. How many syndromes we have? Coordinative syndrome is at most n plus 1, a number of values. It's 0, 1, etc. up to n. And if all vectors were active and all of them send 1 at this position. So therefore, the number of syndromes not more than n plus 1 to the power r. So we have then, we need that different vectors have different syndromes. Then number of syndromes should be more than bigger or equal the number of vectors. Therefore, we have this inequality. Or if you take log, we have this r minimal number of questions is at least n divided on binary log n. And my goal is, because I will mainly only talk and say what are results, and it's only the case when I will give a proof, because the proof is, I think its proof is rather easy, but still a nice proof. So this this is twice worse than it was received by Erdős and Renyi. Okay, oh, it's empty. It's, don't take, Yes. Is this, and so let me check. Hope. It's not empty. I'm sorry. It's not empty. It just, I eventually erased one page. And I don't know how to do it from the screen immediately. If you can follow me, just wording, let me explain what is missing here. The missing part is the following. There is a rather useful notion in combinatorics. If you have a finite metric space, it's better to think about finite. Just do not think about finite, because we don't need more general case. We have a finite metric space, and we call it metric dimension, the minimal number of points within this metric set with such a property that every point of this space can be uniquely recovered by distances to this given set. If you think about non-discrete case, think about plane. Usually Euclidean plane. Then what is metric dimension of this? Of course, 3. 2 points is still not enough. If I have 2 points, then I have third point, and I know distances for these 2 points. I know either the point x or symmetric, mirror symmetric for these 2 points, x prime. But if I take 3 points, then it's enough. In n-dimensional Euclidean space, its metric dimension will be n+1. If you have n+1 points in general position, then distances to these points is enough to recover the unknown point. So it's called metric dimension, and it's formally appears in the beginning of 70s in graph theory. Implicitly, it was already in this paper, which I already mentioned, Erdős and Renyi in 1963, when they considered the particular case of the Hamming space. But that's what I'm talking about. I'm going to talk right now. So consider the Hamming space, and then check that, of course, this scalar product xi, which we know, is the same, in fact, as the Hamming distance between vectors x and I, in the following sense. The Hamming distance between vectors x and I is weight of x, I mean number of ones in x, weight of ai, minus 2 times the cardinality of their intersection. So, and we know the cardinality of their intersection. Of course, we know the cardinality of ai because it's what we decided to choose. And the only unknown thing is the cardinality of x. For this, we need to ask one question. What is intersection? What is just intersection with the whole space? Or what is a scalar product with vector of all ones? So, so we may, instead of thinking about what is the minimum number of questions, we may ask the question, what is the metric dimension of the binary Hamming space? And then I would like to show that the metric dimension cannot be not the number of points is at least n divided 2 times n divided on log n. And there were some trivial part which shows that repeat the same arguments, but with vectors ai. And the only thing is that what I would like to say that syndromes or distances to my vectors which I choose ai. In this consideration, it could be arbitrary, 0, 1, etc. up to n. But we know that in fact, if the almost all distances is roughly around half of n, and I'm going to use it in the following way. I'm sorry for missing part, but I'll jump to this way. Consider our chosen points. This is, in some sense, metric basis of this Hamming space. The points C1, C2, CR, with the property that we can recover any point of any binary point by its distance to the points C1, C2, CR. So consider a shell around point C1. I mean, consider the sphere of radius r sub 1, which is n minus square root of n times log n divided on 2, and r2 slightly bigger. It's n plus square root of n log n. Then what we know that in fact this shell is huge for large n. That almost all points lie in this shell. roughly speaking, 2 to the power n 1 minus or small o of 1. That's why I choose here log n times log n. So as it's so big, and the number of points, we know that the number of points is not big. At least it's not more than n. So consider the intersection of this. Intersection, instead of considering intersection, consider the union of supplementary sets. And supplementary sets are very small. Therefore, the union of them will be also still a small fraction of the whole space. Therefore, when we consider the intersection, we will have almost all space in this intersection. So check the property that points from intersection can be recovered, only points from intersection can be recovered by their distances to the chosen point C1, C2, CR. Okay, as we have 2 to the power n points, so 2 to the power n minus 1 points, it doesn't matter. Then we can say again that the number of points should be less than the number of distances. But now distances, not in the range from 0 to n. No, they are now in the range of the size square root of n log n. Therefore, the number of distances, different distances, just square root of n log n to the power r. And of course, if we take log, we have exactly what I wanted to have. 2 times n divided on log n, and this log n is small value. So that's the Erdős and Renyi, they used other proof based on information theory technique on entropy. I think that if try to go into details, that maybe it appears the same proof, but I like this proof because it's explained that everything is just because we should be not so easy with calculations of number of distances, because almost all distances are in this range. So how to construct such a set? It's real construction. There are 2 different constructions. Cantor and Mills gave recursive construction. Lindström gave explicit construction, but in fact, it's the same. So let me go ahead, because I'm going to go to explain what is cover-free sets. They're standing in the title, but we don't touch yet this this notion. By the way, why I love different approaches to the same problem, and even if it's different statements of the problem, because with counterfeit coins, it's not clear how to generalize it. But if to think about metric dimension of the binary Hamming space, then the natural question is, why binary? Why not consider QRE Hamming space? And then Volodya Lebedev and I, we gave a conjecture that the dimension will be, again, 2 times n divided on log n, but log should be QRE in this case. And we prove it for dimension 3 and 4. For almost 20 years, the conjecture stayed unproved. And then Nikita Polyansky, with his co-author, they proved a year ago that, yeah, it's true for general Q. And it's a nice paper published in Journal of Combinatorial Theory. So you can find it just by search. So now I'm going to approach the notion of cover-free family of sets. And it's also a very nice statement of the problem. It's group testing. Sometimes I'm surprised that people do not think about these natural statements before. Even not think about it as pure and mathematical. At the end, you will see it's very natural mathematical question. No, it was motivated by some ugly practice. It's a paper of Dorfman in 1943. It's the mid of Second World War. And then, and maybe 94, I should check. And then it was a question that many soldiers were ill by some sexual diseases. And how to check? To check every of them, it's time consuming. And what is more important is test consuming. And tests were rather expensive at the time. Therefore, what Dorfman suggested, to take a blood from group, not from a single soldier, but from a group of soldiers, put it in one test. And the property of the test was that even at least one soldier is ill, then the test is positive. If no one, then the test is negative. So that's why it's called group testing. And of course, this is the problem from one of the third problem from which I started, means that there is a set X of ill soldiers, and there is groups which we choose in advance, A1, A2, AR, in advance, and that's for this property, it's called non-adaptive search. And then for every test, we know only if the intersection of X and AI empty or not. So on the language of multiple exit channel, it means that it's disjunctive channel. It takes the following Boolean sum of our vectors AI with coefficients xj. So, and finally, I would like to think now not about rows in my, of course, I will put the characteristic vectors of A1, A2, AR as rows in my matrix H, but now I want to consider matrix H by columns. And let H1, H2, H sub n, their columns. Then the syndrome is, of course, just the Boolean sum of this column vectors Hi. And as Xi is 0 and 1, I may write it this, the sum of Hi for such I where Xi is 1. So that's what we have. And we want to have the different S for different X. And now a very nice sufficient condition to have this property, the different syndromes. What I repeated here, that if the syndromes are equal, then the vectors are equal. Of course, on the assumption that number of ones in both vectors is at most t. So what is sufficient condition? I wrote this formally, and in a minute we will see it's a nice form of this. Consider on these columns, and let the columns have this property that if I take T columns, and I have a different columns from these T columns, I take column HI and I take a set of columns HJ. Then there should be coordinate K in which, or say row K, in which column HI has 1 and columns from the set J has zeros. Of course, let's replace these vectors, common vectors, to sets. But now they are not sets on endpoints. No, it's sets on R points. But still are sets with which property? That no set is covered by the union of T other sets. This notion, mathematical, appears only in Erdős and other, and the whole paper in 1982, despite that the same codes, the same objects, were investigated in group testing. It's part of combinatorics, in fact, encoded here as superimposed codes. But no one came up with this nice formulation of this property, because they use it, but they don't observe this nice formulation of the property. So, in fact, if we run back to the beginning, then these results, they are for cover-free sets too. There is this sufficient condition appears to be almost necessary. Almost means that if you have a cover-free set, then it gives you a property of different syndromes. But if you have matrix H, which provides you different syndromes property for the size of the sets T, then you have T minus 1 cover-free property. So for its asymptotic should be the same. Or not should be, it's the same. So, and maybe just concluding remarks. The easiest case, as I say, was the when we know cardinality of an intersection by modulo 2. And why we know that in this case is minimal is T log binary log n. Oh, because it's H will known in coding theory as parity check matrix of linear code. And we know BCH codes, which has the parity check matrix with exactly T times log n rows. And on the other side, other hand, the very easy Hamming bound tells us that, oh, it cannot be less than T log n minus constant. And constant is, in fact, a binary log T factorial. So therefore, we know the answer is for this case. And again, why it's better to consider different statements of the problem. For codes, it's natural to ask why we resolved about on the binary codes. Consider some finite alphabet, but maybe finite field, and consider a non-binary case. And the same property that linear combinations, in fact, of T columns of the parity check matrix should be different. And then, unfortunately, we don't know the asymptotic. We know only that it should behave as T times QR log n with some constant. We don't know the constant. We know the constant is the same and equal 1 only for the simplest case, T equal 2, and even the very small alphabet 3 and 4. After that, we don't know. It's again open question. And now the end point is that you may remember that in the beginning, we assumed that the player is a honest guy. And we ask him a question, and he gives us the right question. What happens if he can lie? Okay. No, what? No, it should be. It's missed again. Oh, I'm sorry. Then let me say in words. If the hider, the player, can lie, then it's also very interesting, say, branch of these problems. saying more, say in high words, it means that we think that our measurements may be incorrect. The easiest case is known under the name Renyi-Ulam game. And it became famous, or say well-known, thanks to Ulam, who asked this question in his book. The Adventures of Mathematician. Yes, and then it takes about 10 years to find the exact answer for the following looking very simple question. We have unknown number, integer number in the range from 1 to million. We ask questions, and the answer is yes or no. How many questions we need to reveal this unknown number if the person who gives us answer once can produce a lie? If without lie, then of course binary log of million is 20 questions. Therefore, it's called 20 questions game. So what is the number of the questions when the person could lie? It takes 10 years. And finally, after the solution was received, the people found a very easy way how to solve this problem. And even with more than one lie, through the coding theory results. And for this particular case, the answer is 25. And the explanation is the following, that if the player choose some integer in some range from 1 to n, and he can produce t wrong answers on our questions, then the number of questions is enough the following, is log n, as usual, plus t times log n. So we see that lies, it's not so dangerous. So that's the end of my talk. Thank you for your attention, and I'm ready to ask. The questions may be more difficult than I ask in this my talk.
Okay, thank you, Grigory. Do we have questions?
This is Zoom.
Depends on.
Yeah, maybe. Okay, that's maybe my.
Maybe the common question: what is open button doesn't seem so hopeless?
That's of course reminds the well-known joke when a student approached professor and say, "Professor gave me yesterday the bad problem," and he said, "What means bad?" And the student PhD student replies, they say, "Yeah, because I thought about this problem yesterday evening, even in the morning, I didn't solve it. Moreover, I have an impression that even if I solve the problem, it's not makes me famous." And professor say, "Okay, understood. What meaning the bad problem? What is a good problem?" And students say, "Of course, the good problem when you can solve it in reasonable time, and when you solve it, you become famous." And professors say that, "Okay, I don't know such a problem right now. By the way, if it came to my mind, I will try to solve it by myself." Yeah, but to tell more seriously, your question is very right. And if I'll run through my talk, I will say what I think what is hopeless, and maybe what is not. This part. Dishkov tries to find the final answer for this asymptotic for almost 40 years. Nowadays, we have new guys. We have Nikita Polyansky, Ilya Vorovyov, others. And they even publish a paper when they prove that the right answer is this one, but later on they have found a mistake in their proof. So it's still open. Moreover, I doubt that you see some experience which we have from coding theory is that usually the random coding bound appears to be tight. But in most interesting cases, we don't know if they are tight or non-existent bound are tight. And the most famous gap is the gap for best density for sphere packings, or the Kisin number in n-dimensional spaces. There are two approaches. The random, which gives you some good value, and some sophisticated upper bounds, but they differ very much, exponentially much in density. So that is open, and it seems to me very difficult. In fact, the same gap is here. Again, this is, it was received by random coding. And this is some kind of information theory technique, by entropy technique. Oh, by the way, I forgot to say that this question for cardinality, I said on the, can be generalized on the language at least of multiple X channels for QR cases, and it was open. So my two PhD students, Irina Egorova and Valeria, oh, I forgot the family name, it come to my mind. They did it, they generalized it. And the answer for the QR case, the same, only from, instead of binary case, you have binary log, you have here QR log. But again, it's a gap between probabilistic method or random coding and some attempts to prove that no, we cannot do much better, but usually it's a gap. So this is like a case, but I explained that it's only for binary. For non-binary, we don't know this. Again, this is like a case. We have it for binary. And again, thanks for Nikita Polyansky. Now we have it for QRA, for this case, but not for arbitrary size of the set, not for the case that there is a threshold for cardinality of the set. So to tell the truth, every such result when we usually people cannot improve the random coding bound. Therefore, this is a very good exceptional case, but maybe because it's out of the coding style, because we have too many errors. Usually we have random, and to prove the random is optimal, it's very difficult. So, maybe you know, it's a usual mathematical style. When we cannot solve the problem in its original statement, we try to generalize it, and then try to stem known results for original case to more general cases. in some sense, the case of errors, lies, could be such good generalization, which can produce some new results. So that's what I can say.